So for this one, to find the equation of the tangent line, we need two things. We need the point and we need the slope. So to find the point, we can put 4 in there. So if we put 4 in, we get 2 out. So it goes through the point 4, 2. That's the point of tangency. And to find the slope, we need to find the derivative. So remember, square root of x, same as x to the 1/2. So our derivative would be 1/2 x to the negative 1/2. But we can rewrite that as 1 over 2 times square root of x. Because x to the negative 1/2 just means square root of x in the denominator, or x to the 1/2 in the denominator. So to find the slope, it's just the derivative at that point. So when x equals 4. So square root of 4 is 2. 1 over 2 times 2, we get 1/4 for our slope. This is our point. So we can write an equation of the line that goes through that point with that slope using point-slope form. Y minus 2 equals the slope times x minus 4. We can go ahead and distribute and kind of put this in slope-intercept form. We get y minus 2 equals 1/4 x minus 1. And then add the 2 to both sides. We get 1/4 x plus 1. Is to graph the original function, the square root of x, along with this tangent line. So I'm going to go ahead and graph the tangent line first. We have a slope of 1/4, y-intercept of 1. So start off at 1, up 1 over 4, up 1 over 4, and draw our line. So that's our y equals 1/4 x plus 1. And then for f of x equals square root of x, we could kind of make a table here. If we put 0 in for x, we get 0 out for y. What's another nice number we can put in for x? It'll give us something nice. What's that? 9. Square root of 9 is 3. Anything in between 0 and 9? Joe? 1. Put 1 in there, we get 1 out. Square root of 1 is 1. And then one more 4, right? We can take the square root of 4, and we get 2. That's our point of tangency. That's where the tangent line touches the graph. So the blue graph is square root of x. The green graph is our line. Now you can see right near the tangent line, near the point of tangency, this green line, the tangent line, is really close to the blue graph on both sides. So they're going to be pretty close values. We're going to use this green line to approximate values near x equals 4. So those examples are down here. It says we can use the equation of the tangent line to approximate values of f of x near the point of tangency. So for example, what's f of 3? So first of all, let's put it into our function. So I'm going to put it in blue here. F of 3 means the square root of 3. So if we punch that into the calculator, what do we get? 1.732, right? Now, let's see what we get when we put 3 into the equation of the tangent line. Y equals 1/4 times 3 plus 1. So 1/4 times 3 is 3/4. Plus 1 is 1 3/4, or 1.75. So you can see these two right here are pretty close. Right, and 3 is not even that close of a number to 4 relative to this graph. But those values, those y values, are pretty close. The next one here asks us to try 3.9. Put 3.9 into the original function, so square root of 3.9. If you put that in the calculator, what do you get? 1.974. Yeah, you sure? You positive? Okay. 9748. We'll go ahead and throw that in there. Now, if we put 3.9 into the equation of our tangent line, 1/4 times 3.9 plus 1. For that one, we should end up with, comes out to 1.975. So as you can see here, these two are very close. 3.9 is really close to 4, so that makes our approximation even closer by using that tangent line. So it works for anything that's close to x equals 4. If we tried this when x was like 0, obviously those aren't very close because we have like 0, 1 and 0, 0. But if they're close to that point of tangency, close to x equals 4 in this case, that means our approximation is going to be pretty close. Alright, so what we have down here is a linear approximation formula. But basically, all this is the equation of the tangent line. Right? Same thing we just did. It's just kind of masked as a formula instead of just doing what we did. We used the point slope formula to find our equation. This looks different, but really, in the end, it's the same type of thing. So what we did in our problem was use the point slope form. We had y minus y1 equals the slope times x minus x1. Right? And y1 and x1 were actual numbers that we knew from the graph. We plugged those in, found the slope from the derivative. Well, if we just take this equation and add the y1 to both sides, we basically get the same thing as over here. It's just written a little bit differently. So f of x is like our y value. F of a, well, that's the point. F of a is like the point of tangency. So that's the point of tangency where the lines are, where the line is tangent to the graph. So f of a is just that y value at the point of tangency. The derivative of f of a, that's the slope at the value a. Right? That's what we figured out in our problem up there. Slope. X minus a. And a is our x value, that point of tangency. So it's really the same thing we just did, just written in a different format. This linear approximation formula is just the equation of the tangent line that allows us to approximate values near a specific x value, like we did in that first example. So let's go ahead and take a look at an example here. It says for f of x equals square root of 3 plus x, so that's our function. Find the linear approximation when x equals 6. So the linear approximation, it's just asking for that equation. Right? It's really basically the equation of the tangent line at x equals 6. So this x equals 6, this right here is our a value. In our formula, we've got a and f of a. Right? That's the point where it's tangent. So in our problem down here, the a value is 6. A value is always a nice value. And what I mean by that, nice value, is something that we can plug into the equation and figure out in our head without having to do it with the calculator. Right? We can put 6 into this equation. Square root of 3 plus 6 is just 3. We can figure that out. So the a value is always the nice value. So our first part is just writing that equation. That equation, f of x, is approximately equal to, so that means like the original function right here is approximately equal to this equation of the line. So f of a plus the derivative of f of a times x minus a. So that's what we're trying to figure out. And for these problems, we're writing this equation. There are three things we need. So you can start off writing this for every problem. We need to know what's A, what's f of A, and what's the derivative of f at A. We need those three things in order to write this equation. So A we've already designated as 6, right? That can give us that. A is 6. F of A, we need to figure out. That's all we have to do is put 6 into the function. Right? So square root of 3 plus 6, square root of 9, which is 3. Right? Just like we did at the very beginning of notes today. We're finding f of A, that's the y value at the point of tangency. Then we have to find the slope, which is the derivative of f at A. So before we can figure that out, we just have to find the flat-out derivative. So f of x is the square root of 3 plus x, where that's the same as saying 3 plus x to the 1/2 power. So our derivative would be 1/2 times 3 plus x to the negative 1/2 times the derivative of the inside, which is 1, which we don't really have to write, but just as a reminder, we have to multiply the derivative of the inside, but since it's just a 1x there, the derivative of that is 1. So we can rewrite this kind of like earlier. 1/2, so 1 on top, 2 on the bottom. 3 plus x to the negative 1/2 means the square root of 3 plus x in the denominator. So there's our derivative. But we need to find the derivative when x equals 6. So 1 over 2 times the square root of 3 plus 6. We're going to end up with square root of 9, which is 3 times 2. We get 1/6 for the derivative of f of A. So we have the three things we need to write this linear approximation equation. F of x is approximately equal to f of A, which we got was 3, plus the derivative of f at A, which is 1/6, times x minus A. So this one, we can go ahead and simplify. We don't always have to, but we can simplify this pretty easily by distributing the 1/6. And then we can combine the 3 minus 1. So we get 1/6 x plus 2. So there's part A. There's our linear approximation. This is basically the tangent line when x equals 6 on this graph. Could have done it kind of the same way we did before. What we did just looks a little different. Found out A, the x value, plugged it in, found out what the y value was, found the derivative and plugged in 1/6, plugged in 6 and got 1/6 for our derivative. So that's our slope. So there's our linear approximation. Part B asks us to go ahead and find some of these approximations. Use this linear approximation to estimate what's f of 5 equal to. So f of 5 is approximately equal to, we're just putting 5 into this equation, 1/6 times 5 plus 2. So we could say 2 and 5/6. That's the approximation, but let's go ahead and write it as a decimal. So this one we should get 2.833. Then it asks us to approximate f of 5.9 and f of 6.3. So again, we're just plugging those into this equation of the line, the tangent line. So if we do 5.9 divided by 6 plus 2, we get 2.983. He's not here today. No. Alright. Then if we go ahead and put in 6.3, so we have 6.3 divided by 6 plus 2, we get 3.05. So those are all approximations for these values of the actual function. So this is an approximation of what we would get if we put 5 into the original function, square root of 3 plus x. Now let's compare them to what we actually get. It disappears. So we've got f of 5 means square root of 3 plus 5, or square root of 8. If we do square root of 8, we get 2.828. Right, compare it to the original one, that's pretty close. If we round both of these to two decimal places, we'd have the same answer. If we do f of 5.9, that's a square root of 3 plus 5.9, or square root of 8.9. We get 2.983. And that's exactly the same as our approximation rounded to 3 decimal places. You can see that's closer to 6. That gives us a better approximation. And then our last one, if we do f of 6.3, that's the same as square root of 9.3. We get 3.04959, which just rounds to 3.05, what we had in our approximation. All right, on the back, number 2 here, a little bit different. It doesn't have everything set up for you. You have to do a little figuring out on your own. It says, use a linear approximation to estimate sine of 0.05 and compare the value with the actual value. So, remember I told you before we were going to need to know what's A, what's f of A, and what's the derivative of f of A. The other thing we need to know is what's the original function. And the other problem that was given to us here, it doesn't directly say it, but what function are we talking about here? If we're trying to estimate sine of 0.05. Sine of x. Right, sine of x is our function. 0.05 is what we're trying to estimate. But 0.05 is not our a value. Remember, the a value is supposed to be the easy value, the nice value. So we need a value that's close to 0.05 that's easy to calculate the sine of. So what's something close to 0.05 that we can figure out the sine of? Say it loud, say it proud. 0, there we go. All right. So it's 0. Right, it's close to 0.05, and we can figure out what the sine of 0 is. So 0 is our a value, our nice value that we can plug in easily. So now we need to figure out the other two parts. F of 0, f of a is f of 0 in this case. So that's going to be sine of 0. Since you're all whizzes at the unit circle, what is sine of 0? 0. Good. All right. So sine of 0 is 0. So f of a in this case is equal to 0. Last thing we have to figure out is the derivative of f of x, so that we can find the derivative of f of a. So derivative of sine, cosine. So we want to know what's that derivative when x is 0. So cosine of 0, 1. All right, so we've got our 3 parts. We've got a, f of a, and the derivative of f at a. So this is like our x value, our y value for our ordered pair, and this is our slope. So f of x, that function, sine of x, is approximately equal to f of a, which is 0, plus the derivative at a, which is 1, our slope, times x, minus a. So this one actually simplifies pretty nicely. It's just x. So what this is saying is this graph sine of x, when x is really close to 0, the y value is almost the same as the x value. So here we're trying to approximate the value at 0.05. We want to find out what's the sine of 0.05. Well, that's approximately going to be 0.05. Normally there's a little bit more of an equation that we have to plug it into, but in this case, x value is pretty close to the actual y value. Right? If you think about it, it should kind of make some sense. There's our graph of sine. We're doing this at x equals 0, so at the origin, 0, 0, and the slope of the tangent line is 1. So when it's really close to this, if the slope of the tangent line is 1 at 0, 0, then every point on here is like x equals y. X and y values are the same. So on that line, x and y are going to be pretty close. So we get 0.05. We can go ahead and check in our calculator what's sine of 0.05 actually equal to. Make sure you're in radian mode. So, like it said, 0.04997. So you round it, it's going to round to 0.05. So that's a pretty close approximation. Number 3, again, we're not given our function. What are we looking at here? We are trying to estimate square root of 120. So what do you think f of x should be? Square root of x. Good. All right, so we need that function. We also need to know what's a, what's f of a, what's the derivative of f of a. So for this, then, a, remember, that's their nice value. What's a number that's close to 120 that we can take the square root of? So 121 is a nice value. Close to 120 that we can take the square root of. So that's what we're using for a. F of a, or f of 121, is just square root of 121, which would be 11. And then we have to find the derivative, so we can find the derivative of f of a. Just like the problem at the very beginning, square root of x, same as x to the 1/2. So our derivative would be 1/2 times x to the negative 1/2. Or we could write that as 1/2 times the square root of x. We want to figure out what this is when x is 121. So 1/2 times the square root of 121. Maybe 1/2 times 11, so 1/22. So we have everything we need to write our linear approximation equation. The original function, square root of x, is approximately equal to f of a, which is 11, plus our derivative, which is 1/22, times x minus a. So this one doesn't work out as nice if we go ahead and distribute like some of the other ones we have. We can just leave it how it is. Although this problem's not asking for the equation, we want to estimate this. But if we're asking for the equation, just leave it like this, that'd be fine. Now that we want to estimate this, when x is 120, we're just putting 120 in here for x. So we get 11 plus 1/22 times 120 minus 121. So 120 minus 121. Gives us -1 times 1/22 So we basically have 11 minus 1 over 22. We could write that as 10 and 21 20-seconds. Right. That would be an approximation in fraction form, but if we were to go ahead and write it as a decimal, 10 plus 21 divided by 22, we get 10.955. So either one of those forms. And we can kind of compare it to the actual answer, square root of 120, 10.9544. So this is only like 9 thousandths or whatever it may be off. So this one's pretty darn close. Sorry if you're not finished. For this one, f of x is square root of, or cube root of 3. Value close to 28 that we can take the cube root of is 27. So f of 27 will be the cube root of 27, which is 3. We have to find the derivative of f of x. So remember, this is the same as x to the 1/3. So our derivative is 1/3 times x to the negative 2/3. Or we could write that as 1 over 3 times x to the 2/3. But really what that means is the cube root of x squared. That's kind of the easiest way to figure it out without a calculator. Or you can write it as cube root of x squared on the inside. But if you write it this way, it's the same thing. Right, so it's easier to kind of figure out this way. So if we have 1 over 3 times the cube root of 27 squared, cube root of 27 is 3, 3 squared is 9. So we get 1 over 27 for our derivative. It's easier to figure that out in your head in that order instead of squaring 27 and taking the cube root. So our equation here, f of x, is approximately equal to 3 plus 1 over 27 times x minus 27. We want to do this for 28, so f of 28 approximately equal to 3 plus 1 over 27 times 28 minus 27. So we get 1 times 1 over 27, so 3 and 1/27. So that gives us 3.037. We can compare that to the actual cube root of 28, or 28 to the 1/3. 3.037 if we were rounded.